Okay, guys, so let's take a look at where we're at here with the tree stuff, okay? So we're now at this point, we've got this really good-looking tree that uses our tree node, and we've set up a linked list that's ready to hold on to node values should we need it, okay? And we will need it, obviously. So we came down to this toString method that we are going to rely on 3 methods. So yesterday I suggested that why not reorganize this code a little bit so that it's just sort of optimized this way, that we create a string that says tree traversals, and then we're going to add to that string the pre-order, post-order, and in-order traversal. We'll make a call to those things. Those things will return a linked list, and then that linked list will be turned into a string. So here, for example, let's write what one of them will look like. It'll be public linked list called pre-order. Okay? Not per order. That's a typo. Okay? And obviously, it's going to return our list. That's our global object, is the list object. But we got to do more than that. That's not enough, obviously. We're going to fill that list first with all the nodes in the pre-order traversal. So I'm going to explain what that is in a second. Before we do that, we're going to essentially clear the list by making it a new linked list. Come on, computer, catch up. There we go. Okay, of generic type T. Okay. So we will instantiate the list. That will be useful in case it already had something in it. So that will essentially rebuild the list, then we'll fill it up, and then we'll return it. Okay? The filling will take place through a recursive method. So we're essentially, again, using pre-order as a wrapper method to hide the fact that we're going to be doing something recursively here. Okay? And you can go ahead and copy and paste this, because this is going to happen for pre-order, post-order, and in-order. All 3 of these methods will do the same thing. Pre, post, and in-order. All 3 of those methods will instantiate the linked list, do something, and then return it. Okay? Now, the linked list is a global object, so we don't have to pass it back and forth from method to method. It's unnecessarily passed. But what we are going to do, so for example, in the pre-order method here, is we're going to call pre-order, okay, and this is going to be recursive, so we'll call it pre-order recursive, okay? And what we pass it is our root node. Okay? So this will be a method that we're going to write. The pre-order recursive starting at the root. You will then do this with post-order recursive. And down here with in-order recursive. So those will be 3 helper methods that we will put in that will be recursive, that will help these 3 methods, these 3 wrapper methods, do their job. Okay? And they will be private methods. They will be hidden within the class. These are the public methods that give you all the nodes in post order based on returning it as a linked list. Okay, so you can go ahead and create these 3 methods. You can use the light bulb if you want, or you can just manually key them in, whatever you feel is useful. They'll be void methods. They won't return anything. Okay? And here they are. Whoops. The only thing I would suggest about these 3 recursive methods is let's not call it root as a parameter. I know that's the one we passed it, but let's just call it current. It's just a current node. It's a current node that we're going to be looking at recursively. Now, here's the good news. What the code we're going to put in here is really short. It's like 4 lines for each of these. But the concept of what's going, like any recursive method, they're short methods. But like with any recursive method, it has a little bit deep of an understanding of what's going on there. So I've made a little animation to try and demonstrate what's going on here. All right? So let's take a look at trees in this context. Okay. There we go. To travel a tree, or to traverse a tree, means to visit every node. And that's what we're trying to do here. We're trying to visit every node. The traversal algorithms are essentially the same whether the tree is in order or not. Our tree happens to be in order, right? The way we designed it as a binary tree is when we insert a node, it gets inserted into its correct spot. But if we just randomly inserted the nodes, and we didn't worry about that, the traversal would also be the same, okay? Now the reason you'd travel a tree would be printing the nodes, counting the nodes, searching the nodes, etc. We happen to be using it right now for printing purposes, for turning it into a string. But the three traversals, pre-order, in-order, and post-order, are very similar to what we studied in stacks and queues about those different forms of equations, okay? But this is a recursive process. Okay, so here's the animation. When going in pre-order, the way it works is you start by visiting the current node. By visiting, the way you could describe that is that's when it gets outputted. Or, for our case, that's when it gets put into our linked list. So the first thing we do is, based on the node we're at, put it in the list or output it. Then travel the subtree to the left. When you're finished traveling the subtree to the left, travel the subtree to the right. So the way this would output would be, because where do we start? We start at the root. So I would output the root, then I would go to the left subtree. Now this is recursive, so the algorithm starts over again. So I start off at 1 again. I output the node. And then I go to the left subtree. I output the node. Now from 10, what's the left subtree? Null, right. So I wouldn't need to output the null. What would be my next instruction? Go to the right. What's the right subtree from 10? Null, so I don't need to output that. So then this would be, 1, 2, 3 would be done recursively at this level. Now I'm back here at this one. The next instruction, I've just finished 1, and 2, I finished going the left subtree. Now I go to the right subtree. So the next node that would be outputted would be 40. Then 40 goes to the left subtree, and then it goes to the right subtree. And then this is done recursively. This one's done recursively. Now I'm back at the root. I've done the whole left subtree. Now I do the whole right subtree. So in a pre-order traversal, the nodes would be outputted in that order: 60, 20, 10, 40, 30, 50, 70. Okay, I'm just going to skip the code because we're going to key in the code in a second. In a post-order traversal, it's the same 3 instructions, but in a different order. Now I visit the left, then I visit the right, and then I output the node. So starting at the root, first thing I got to do, go to the left. When I'm at the 20, go to the left. When I'm at the 10, go to the left. Oh, that's a null. So instruction 1 is done. Go to the right. Oh, that's a null. Instruction 2 is done. Instruction 3, output the 10. But then that's done recursively. Now I'm back here at the 20. I've now gone to the left, so now I go to the right. And the recursion starts over again. So the output of the nodes in this case will be in this order. So that's weird. That's what the post-order traversal will output. 10, 30, 50, 40, 20, 70, 60. Okay? Notice how that kind of does that output. 10, 30, 50, 40, 20, 70, 60. Whoops. So that's the post-order traversal. It's the same 3 instructions, but in a different order. And guess what? The in-order traversal is the exact same 3 instructions in the final different order. So go to the left, then visit, then go to the right. Watch how this one works. So from the root, I go as left as I possibly can to 10. Output it. Then, from the 20, because I'm back at the 20, go as left, pardon me, now I've gone from the 20 as left as I can. visit the current node at 20, now go as right as I possibly can. But when I get right here, I got to go left again. Then I got to go to 40. Then I got to go right again. Then I got to go back to 60. Then I got to go right again. Notice something about the in-order traversal, the way it outputted the nodes. Does anyone notice anything about them? They're literally in order, okay? So that's the way it essentially works, okay? So let's key this in. I know it's a little bit tricky to grasp right now, so let's try this, okay? Let's try and get this done. Yeah. Okay, so we'll start with the pre-order traversal. So first of all, we have to deal with leaf nodes. If current, whoa, that is all capital letters. If current equals null, okay? So if current is null, I've reached a leaf node. So that's when the recursion should stop. That's a base case. So I'll return right here because it's a void method. So this is a base case. That's what stops the recursion, right? Is when I've reached a tree or a leaf node. I'm done. The recursion should stop at that point, okay? Now, according to pre-order, what I now need to do is I need to add the current node to my linked list. Now, we have various ways to add a node to a linked list. But I'm going to actually make a suggestion right now. Could you guys just take a second to open your linked list class? This will only take a second. So go to your linked list class. And let's add a simple method to this thing. Let's add a simple add method. So public void add t data. Let's just be, when you add to a linked list, what would be the instinctive way it would be added? To the back, would you say? Just always add it to the back? So let's call insert tail data. Let's just call that. Now we could have called that back in the tree class, but I like just keeping it simple sometimes. So let's just use that, and let's just use this new add method to add current, okay, dot data to our linked list, and we have to make one quick cast as data type T. Okay, did I go too quickly there? Okay, so let me just recap. In the linked list class, we are using this add method right here to add using insert tail, and then I'm just making it simpler on me here so that I'm just adding the current data to the linked list. Okay, that's what I'm doing. So if current is null, return. Otherwise, add it to the linked list. And now comes my recursion. Now I do a pre-order recursive call to current dot left. And then I do a pre-order recursive call to current dot right. Okay? That's what it does. It visits the node, and then it visits the left subtree, and then it visits the right subtree. And that's it. 4 lines of code to do a pre-order recursive. Okay? Got an error, Mika? Actually, since we're here, I'm going to suggest we add one other little constructor to our linked list class. So if you wouldn't mind, just jump over to your linked list class for a second. This will just take a second. Let's make a third constructor, public linked list. You'll kind of see why later. From a linked list. Make a linked list from a linked list. Okay? There's a good reason for writing this code. We'll get to it later. So what we're going to do here is, when past a linked list, turn the current linked list into the same thing. It's like a clone kind of a thing. So this dot destroy will destroy the current linked list. And then we'll just loop through linked list dot length back up there a bit, and we'll say this dot add linked list dot get spot I, and we have to make one little cast to data type T. Okay, so this is what I'm proposing, is just this little constructor here. Just add this little constructor right there. My little drawing software is not working well, so add that constructor. It's going to come in handy, trust me, okay? Trust walks. So a third constructor. So we have the default constructor. You can just make a blank linked list. We have a constructor that allows us to build a linked list from an array. And then this one, which builds a linked list from another linked list. The reason why this one will become useful is because we use the linked list for inheritance. That's why, but we'll get to that in a little bit. It's going to be cool. Okay, anyone not got that? Back to the tree class. So now, here's how easy this is now going to be. These 4 lines of code are going to be the exact same 4 lines in the next 2 methods as well, but in a slightly different order. But however, it's important that you don't make this mistake, because you might want to just try copy and paste. But when we copy and paste, we're going to have to change the name of this, not as pre-order traversal, but to the other ones. So I'm going to actually suggest not copying and pasting here, because otherwise, well, actually what I'm going to suggest is copy the first 2 lines. Go ahead and copy the first 2. Okay? But the other 2 I'm going to suggest we actually key in, because a copy paste might actually mess it up. Okay, so with post order recursive, not pre-order, but post, we put the adding of the node as last. What goes before it is a post order recursive call to current.left, and then a post order recursive call to current.right. Oops. Okay? So that's how post order recursive works. You still have the base case first, then you visit the left subtree, you visit the right subtree, and then you add the node. Notice how that's slightly different than the one above it. In the one above it, this will always be first. I visit the node, then I go left, right. Now, this is actually super easy to remember. If you think about the wording itself, pre and post. Step out of computer science for a second. What does the word pre mean? Before. What does the word post mean? After. Where is this line being put amongst the 3 instructions? It's being put first, or it's being put before. Where is that line being put in the post order traversal? It's being put after. And notice these always just go left, right, like you would imagine they would go, like you're taught to read in North America. You're taught to read from the left to the right. So guess where it goes in order traversal? What would the word in mean? What's another version of the word in? In between, exactly. So it's actually fairly easy to remember in that one too. So in order recursive, we first go to in order recursive to the current.left. Then we visit, then we go to the in order recursive to current.right. Okay, so here you can see with in order, the part where we add it is in between left and right. Okay? Now you still might be difficult to grasp how this works in terms of a tree. But the actual code lines are fairly simple because of the recursion taking place. Recursive algorithms are always going to be simple in their design. But this now, theoretically, should work. We now have everything in place to execute our toString method. It will output them in post, pre, and in order. If now we take a look at our main, if we go to main, we now have a tree built of integers We executed a search, but let's do something better than the search. We knew the search worked. Let's just output the tree at this point. So we can actually output, because we now have the ability to turn the tree into a string, we can output the tree. So let's try this. Let's run this code and see what happens. Why, look at that. We have some output happening. So here's what it's saying. So let me take a second to try and draw this. Okay? So the way our tree was constructed, according to the instructions we gave it, was it started with 50. That'll be our roots. Then it inserted a 30, and the 30 is less than 50, so it went there. Then it inserted a 90. The 90 is greater than 50, so it should have inserted it there. Then it inserts a 40. The 40 is less than 50, but greater than 30, so the 40 should have gone there. So that's what our tree should look like. So let's see what the ordered traversals does with this. According to the first traversal, it says, output this in pre-order. So pre-order means, 1, output the current node. We're always going to start at the root. It's the only place to start. So you start at the root, output 50. It did. Then go to the left, and the algorithm starts over again. So the algorithm says, output the current node, 30. Then it says, go to the left. When left is null, it just returns. Then it says, go to the right. The algorithm starts over again. Output the current node. Then go to the left, null. Go to the right, null. Just like here was null. So it's done left, it's done right. That recursion is complete. Now it's gone back to this one. It's gone all the way to the left. It's gone all the way to the right. This recursion is complete. Now it goes back to the original recursion. It's gone all through the left. Now it'll go to the right, goes to the left, goes to the right, outputs the node. So you can see how the pre-order traversal works on that round. Okay? Now, let me backtrack. Can't I undo? Come on, let me undo. Oops. I got to clear it. Silly, silly software. All right. Okay, so now I think it's worth it for me to still draw out this tree. 50, 30, 90, 40. Okay, so let me run the post-order traversal. In post-order, the way it works, post means last. So starting at the root, it goes to the left, restarts the algorithm, goes to the left, it's a null, so it's done. Then it goes to the right, restarts the algorithm, goes to the left, goes to the right, and once it's gone as far left and as far right as it can, it outputs the node, 40. At this point, this recursion is done. Now it goes back to the previous recursion. It's gone to the left as far as it can, it's gone to the right as far as it can, so the next instruction, output this node. That recursion's done. Now I'm back here. I've gone left as far as I can. Now I go right. Recursion restarts. Go to the left, go to the right. I'm done this little recursion. This guy's done. Output that node. Finally, I'm back here at the original recursion. I've gone left as far as I can. I've gone right as far as I can. Output this node. And notice how our post order is working there as well. Okay? So, cool. It seems to be working. Okay? Finally, I still think it's a useful exercise. Redraw the tree. How does it work with in order? Okay, here's how it goes with in order. With in order, the output is in between. So we're starting at the root, go to the left, restart the recursion. Go to the left. Okay? I can't go left anymore. The next instruction in between is output the node. So at this point, it outputs this node 30. But now it goes to the right. It restarts the recursion. Go to the left, output the node, go to the right. Right's a null. This recursion is now complete. Now it's here. It's gone to to the left, it's outputted the node, and it's gone to the right. This recursion is now complete. So now I'm back here at the original one. It's gone to the left as far as it can. The next instruction in between is to output this node. And now it goes to the right. Restarts the algorithm. Go to the left, output the node, and then go to the right. And we're done. That's how the 3 traversals work. Okay? Yes, by the way, if you were thinking, I wonder if these pre-order, post-order, and in-order are related to that stuff we did with the whole math thing, with the equations. Do you guys remember those ones? We talked about it yesterday. Nick, was it you that pointed that out? That there was that you saw pre, post, and in what? Prefix, postfix, and infix. That's right. Absolutely. That's how they evaluate those. They put them in trees and then run the traversals, and it works. Okay? All right. So that's pretty cool that we've got these trees that can do this. Okay? And I think, for the most part, that's all I wanted to do with trees with you guys, was this concept. Okay, I have a little bit of an animation just to wrap up today, and a little bit of theory as well on this, just a little bit. Okay, so hang on one sec. Okay, so with an unordered tree, that's not what we built, by the way. We built an ordered tree. Mika, I see your head. Let me just finish this, then I promise I'll come give you a hand. Okay? With an unordered tree, you can put values anywhere. But an unordered tree is not that useful to you. Okay? With an ordered tree, there's only one spot you can put a node. And that's what we built. We built an ordered tree. So here you can see, if we do 15, 8, 12, 19, 5, 23, it would do it in that way. 15, 8 is less than 15, 12 is less than 15 but greater than 8, 19 is greater than 15, 5 is less than 15 and less than 8, and 23 is greater than 15 and greater than 19. Okay? That's the way it builds trees in an ordered tree. If it receives the numbers in a different order, it will build a different looking tree. Sometimes programmers will shorten the binary search tree to just a BST. BST for binary search tree. Okay? By the way, you'll notice why it's called a binary, often called a binary search tree, is because it's so efficient at searching. Okay? We wrote that search algorithm. We wrote the insert, we wrote the tree class, so this is all in the notes. Okay? We've already done this. But I just wanted to wrap with a little bit of tree theory. Okay? So there's another traversal that we didn't code called the breadth first traversal, in which you visit the nodes by level. Okay? So for this one, for example, you would, for each level, output the nodes, right? Like that. There is no simple recursive way to do this. This would require a larger algorithm. Okay? To do this one, most likely, I don't know if you can read there, the most common way that this is done is to use a queue object and queue in the nodes as you travel through it. You don't need to know how to do that for, I don't even think you need to know the traversals for IB, to be honest with you, but you will learn these in university, so I'm going to teach them to you because it's better to know this. Okay? But that's a theory of another traversal, is the breadth first traversal. Okay? Now, as well, one thing you don't need to know in IB, which seems like something you should know, but is actually very hard to do, is how to remove nodes from a tree. Now, you might think that that's an easy thing to do, but it's actually not, because there's 3 different scenarios here for removing a node. 1, if the node has no children, that's actually easy. That's just, what kind of a node would have no children? A leaf node, or it's also possible that a root node could have no children, if it's just one node tree. Or the node has 1 child. Would that be an easy removal? You could just switch them, right? Couldn't they just be switched and that'd be okay? But if they have 2 children, we have to do what's called a rotation of the tree. Okay? To remove a leaf, you just kill it, right? That's easy. To remove the 1 child, just replace the 2, like basically swap the 2 node values and then delete the other one. Okay? But with 2 children, it's a little more difficult, okay? So removing the 10, easy. I just set this left pointer, or this left reference, to null, okay? In this case, to remove the 2 from this tree, it's pretty easy. All I do is redirect this guy around that one, redirect it, and then, like we did with linked lists, and then it's no longer available. So removing 0 children, easy. Removing 1 children, easy. Removing 2 children is much more difficult, because in the middle of a tree, you've got to kind of look at the nodes below you, and you'd actually have to do what's called a rotation of some of the parts. I'm not going to teach that to you. It's a little more challenging, and we kind of don't have time. Like, that would take a couple classes to sort of work the algorithm out of that. But you don't have to know that, okay? That's what we needed to know about trees. Now, before we leave trees, though, let's go with a super cool example. Let's just fluff up our example a little bit, okay? But to do this, I'm going to ask you guys to make a quick modification to your stack class. Hang on one sec. I'm just going to... Okay, here's what I want you guys to do, real quick. Go to your stack class. And in your stack class, let's add a second constructor to the stack class. Public stack. We can build a stack from a linked list. Let's just call it list. Okay? Here's all you need to do. Make a call to the superclass and give it the list, which is, by the way, why we wrote that method. So we're going to build this into the stack class that you can make a stack from a linked list. Okay? Then, go to the queue class. We're going to do the same thing. In the queue class, also make a second constructor. Public queue from a linked list called list, and same line. Just make a call to the super constructor and give it the list. Okay? Yeah? You guys got that? Anyone need a minute? So both the stack class and the queue class now have those 2 constructors as well. Okay? All right, let's get super cool. Go to main. Let's rewrite our code in main. So let's start with an array. Let's make a string array. String array called array equals, and we'll just do it this way. We'll feed it some stuff. Why don't we feed it, let's be simple. Let's just feed it, I don't know, letters? Or do you guys want to do words? If I do let's do random words. Random word. Jack. Mayonnaise. That's easier for me to spell. Okay, mayonnaise. Is that right? Okay. Erickson, random word. Okay. Jesse, random word. That's not that random. That was the one you used before. Okay. Hang on, I got to move down the line. Kyle, random word. Mika, random word. What? Oh, XIA, is that right? Okay. Nick, random word. Super. Aiden, random word. What? Spell it. Wow. Okay, good. So we got our random array, sort of. Now, from that array, let's make a linked list, data type string called list equal to a new linked list, data type string. We've got a generic linked list. This should work. I might have to import it. But, whoops, I imported the wrong one. Not that one. I want to import my linked list. from the collections package. There we go. And since we have the constructor, pass the array to it when we construct it. So this linked list will be constructed from the array, right? Because we have that constructor. Then, let's make a stack of data type string called the stack, equal to a new stack, data type string. And let's pass it the list, because we've built into the stack class the ability to construct the stack from a linked list. So we turn the array into a linked list, we turn the linked list into a stack. Let's make a queue of data type string called the queue, equal to a new queue, data type string, and let's pass it the stack. Because of polymorphism, a stack is a linked list, and because a stack is a linked list, it will call the constructor building it from the linked list. And then finally, we'll make a tree called of data type string called the tree. Let me just space this out a little bit. Oops. It's easier to read. So I'm going to make a tree equal to a new tree, data type string, and I will call the constructor and pass it the queue. Due to polymorphism, a queue is a linked list. Uh-oh, what happened there? Oh, we don't have that constructor yet. Oh, I think we better have it, because all I wanted to then do was output the tree. So we have one job left to do, writing a constructor in our tree class that takes a linked list. Because look at this. This is all the weeks of work coming together here. We start with an array. That's grade 11 content. We're past that. We turn the array into a list, a linked list. We turn the linked list into a stack. We turn the stack into a queue. We turn the queue into a tree and output the tree. But for this to work, we need a constructor within our tree class that does this. So let's, anyone not on that? Anyone not got that? So let's jump to our tree class to add that constructor. Public tree takes a linked list called list. Okay? Actually, let's call it so that it's just a little bit easier. Let's call it linked list, because I don't want to conflict with that one, which is also called list. Okay? Anyone have an idea how this would get done? How could we do this? Well, we're constructing it, so let's set the root, not the rot, the root to null. Then we just loop through our linked list, so through linked list dot length, and we say this dot insert list dot get spot I, and the only other thing we need is to cast it as data type T. And we've got it. That's the constructor. The constructor just sets the root to null and then loops through the linked list, inserting all the nodes. And remember, that's done recursively. Okay? As it goes and gets them from the linked list. Now, if this works, that's some serious bad you-know-what code going on here. Let's see. We're gonna get a crash? Ah! Correct. Linked list dot get. Good call. Holy moly, it outputted a tree. Look at that. It outputted a tree. And look at the in-order traversal. It's in order. Ah. How do you say that? Aiden, how do you say that? Dinosaur, hypoxia, mayonnaise, super tree. Is it ironic that these are the last two words in this example? Because you guys did a super job making this tree. And it's almost time for the bell. What a finish.